Hello everyone, welcome back to our network security course. So far we were talking about security in different layers. We talk about application layer security and transport layer security. So now it's a good time to conclude our discussion by talking about network layer security. So how can we provide confidentiality at the network layer? This is our main problem. The sending entity encrypts the payloads of all the datagrams it sends to the receiving entity. So that is the idea. The encrypted payload will be TCP segment, UDP segment, or ICMP message, and so on. So network layer security provides a blanket coverage. Network layer security can also provide source authentication. The receiving entity can verify the source of the secure datagram, which is important. It also provides data integrity. The receiving entity can check for any tampering of the datagram. Also, it provides replay attack prevention. The receiving entity detects duplicate datagrams inserted by an attacker. So, network layer security is a good thing actually. So, we will talk about the IPsec and VPN. And the VPN is actually an application of IPsec. So, how to provide security of a network? A solution is developing a private network. Of course, if you trust everybody in the network, then it is a secure network. So it will be a disjoint network from the public internet. A standalone physically independent network. Routers, links, DNS infrastructure, etc. are completely separate from the public internet. Some companies do that, but or at home you can do it with a few computers, but for large corporations that will be a costly solution. The alternative solution is to create VPNs, virtual private networks, over the existing public internet. The inter-office traffic is encrypted before it enters the public internet. So IPsec provides security at the network layer. It provides confidentiality, source authentication, and data integrity. IPsec secures IP datagrams between two network layer entities, for example hosts and routers. IPsec is also used for creating virtual private networks, VPNs, that run over the public internet. So for this reason, this is why we say VPN is an IPsec application. So we have a picture here. This actually summarizes almost everything that we can say about a VPN. So in this picture, we have the headquarters of a company here, and it has a branch office here. So, or if you think about university, we can think about this as Middle East Technical University, and this is our Northern Cyprus campus, for instance. So, people inside this network can communicate with each other because this is a private network, so you don't need to encrypt IP payload here. But since the branch office is in another, for instance, country or in another city and so on, the payload from this headquarters should go to public internet and then reach to the branch office. So for this reason, you actually prefer network layer security. So in this picture, you will see that we can do this with routers that supports IPsec, and of course, let's have the that supports also IPv4 or IPv6. And this is not, of course, the only thing that we need, because a lot of people also, for instance, in this picture, the salesperson of this company leaves the company and goes to another city or country. So, for instance, they are staying in a hotel, so they also want to securely communicate with the headquarters or the branch office. So if we want to also give the same example for our university, these could be academics or students who also want to connect to the main campus computer, or use the services provided at the main campus. So, and in this picture there is only one salesperson, but there can be many different people. So what you do is, before this person is leaving the company, they install an IPsec in their laptop. So their laptop supports IPsec at this point. So you put the cryptographic keys and so on here, which we will be talking about in a minute. So what does this follow? So this router actually acts like a normal router inside the headquarters or inside the branch office. But once somebody in the headquarters wants to communicate with the salesperson here, they had to send this IP package from here. So you have IP header and payload, and assume that the payload is not encrypted at all. So just TCP or UDP packets. So the router now knows that this packet is sent to the salesperson, and automatically with IPsec it encrypts this payload. So now this payload becomes an IP header, IPsec header, and encrypted payload. So it is sent through the public internet, and since this data will traverse a lot of routers through the internet, since the IP header looks like a normal header, this router doesn't have to support IPsec at all. But on the receiving side, the IPsec should be supported, so that once the laptop notices this IP header and IPsec header, they're able to decrypt the secure payload and this way obtain the data. So this way we can have security at the network layer. So this slide actually summarizes what I've said so far. Let's read them. Two hosts in a branch office send IP datagrams to each other. So there is no IPsec because both of them in the same office. But when a host sends an IP datagram to another host within the institution over public internet, the gateway router converts IPv4 datagram into an IPsec datagram. From the perspective of a router, an IPsec datagram is an ordinary IPv4 datagram. So, as I told you, the middle router doesn't need to support IPsec at all. The payload of an IPsec datagram includes an IPsec header. The payload of an IPsec datagram is also encrypted. The client operating system decrypts the payload and passes the unencrypted payload to the upper layer protocol like TCP or UDP. So IPsec is a protocol suite. There are two principal protocols here: authentication header protocol and encapsulation security payload (ESP protocol). AH protocol provides source authentication and data integrity but not confidentiality. So it is like message authentication codes. You have the source authentication and data integrity but no encryption. But since you're getting all this trouble, why only do that? You can also get free encryption. So most of the time ESP is more widely used than AH. And ESP protocol provides source authentication and data integrity and confidentiality. So the only difference is that here you also have encryption, most probably with AES block cipher. So now we can talk about security association, which is shortened as SA. A security association is a logical connection between two entities in a network. SA is set up before sending IPsec datagrams. This is what I was talking about. So the salesperson with the laptop should set up this SA before leaving the corporation, so that they can send IPsec datagrams. SA is from source to destination. This is important. For this reason, when two people communicating, you have to perform two SAs from one source to destination and that destination to the source again. The figure below shows SA from R1 to R2, so you will need another one from R2 to R1. Okay. So, in the picture, assume that there is bidirectional IPsec traffic between headquarters and salesperson, headquarters and branch office. So this is actually what happens in real life. You almost all the time have bidirectional traffic. You rarely have one directional IPsec traffic. So now how many security associations, SAs, we need? Note that an SA is always from a source to destination, so there are two SAs between the headquarters gateway router and the branch office gateway router, one in each direction. But you also have n salesperson, so you need two for every n people. So in total, for this example, we need 2 plus 2n SAs. So in general, if n people want to communicate, you have 2n SAs. Note that not all traffic sent by the gateway routers or hosts will be IPsec secured. A security policy database, SPD, indicates what types of datagrams are to be IPsec processed and which SA should be used. This is a function of source IP address, destination IP address, and protocol type. So let's go back to the picture here. Yes, so when you're sending some data to the internet, here the database checks if it is needed to be IP secured or not. So for instance, if you just want to visit a web page, since you haven't agreed on an IPsec protocol before, so there's no need to send it with IPsec because the other party won't have any decryption key to communicate with you. So this router checks the database and look at the source and destination IP address and the protocol type, and then decides if it needs to be IP secured or not. If it's IP security is needed, then the encryption is performed here, so it's sent as a secure payload. But not everything is sent with IPsec. That is what this slide is trying to tell. So, essays state information maintained by R1 into, so in the database we are keeping essay, and the essay contains this information, a 32-bit identifier for the essay, and it is referred to as security parameter index, SPI. The origin interface of essay, in our example the IP address of here, and the destination interface of essay, that's the IP address of this router. Okay. And it also keeps encryption type and encryption key. For instance, if you are using AES 256, you first keep that information and also keep the encryption key. So you also need to give that encryption key beforehand to this router so that they can decrypt. The type of integrity check, most probably HMAC, the authentication key, and so on. So this kind of information are stored in an essay, and they are put in the database here. State information is necessary by R1 when it needs to construct an IPsec datagram for forwarding over the essay. State information is used for determining how R1 should authenticate and encrypt the IP datagram that arrives at R1. R2 maintains and uses the same state information for this essay and in a similar way. Routers and hosts maintain state information for many essays. Example, the headquarters gateway router maintains state information for 2+2n essays. The state information are stored in Security Association Database, SAD, a data structure in the entity's operating system kernel. So let's look at the IPsec datagram. Two different packet forms there are, and these are called tunnel mode and transport mode, but tunnel mode is more widely used. So below is an IPsec datagram format. This is actually the whole picture, but let's start with from small parts to the and start with the original IP datagram and see how all of this is constructed. Okay. So assume that router R1 receives an ordinary IPv4 datagram from host this IP. Okay. In the headquarters network. It is a destination of this IP address in the branch network office. So below is how the router R1 converts this original IPv4 datagram into an IPsec datagram. So originally what you have is original IP datagram payload and original IP header. So R1 adds an ESP trailer field to the back of the original IPv4 datagram here. Then encrypts all of this. The result is encrypted using the algorithm and key specified by the essay. Again, I told you most of the time people use block ciphers and most probably AES. But of course, you can also use Cha-Cha and so on. R1 adds the ESP header field to the front. The resulting package is called an enchilada. So now you have an extra header for this encapsulated message. And the whole thing is called enchilada, referring to the Mexican dish actually, because you know everything is inside of each other and so on. An authentication MAC is created over the whole enchilada using the algorithm and key specified by the essay. So this whole thing, if you are using HMAC, then HMAC is performed and obtain tag is put at the end, like in this picture. So it is ESP authentication. So the MAC is appended to the back of the enchilada to form the payload. Now a brand new IP header is created with all classic IPv4 header fields, normal 20 bytes long, and appended before the payload here. So this is your new IP header. So this is what an IPsec datagram looks like. But let's look at what is inside this header and trailer. So at the header you have SPI and sequence number. This is to prevent replay attacks. And here you have padding information, padding length, and the next header. And we will talk about them, but you know we also talk about padding when we were talking about block ciphers, so you know what it is about. So in general the payload is ESP header, original IP datagram payload, ESP trailer, and ESP authentication field. So source and destination IP addresses encrypted as part of the payload. new IPv4 header, source and destination addresses are set to the source and destination router interface. So this is important. Initially, when this computer wants to communicate with the other one, the source and destination IPs are the IPs of this computer and the other one. But now, since the IPsec encryption and decryption need to be performed, in our new IPv4 header, the source and destination IPs are the IPs of the routers. So this kind of provides a little bit more security if you think about it, because over the internet, the people listening to this communication will see the IP addresses of the routers, not the original source and destination addresses. The protocol number is also set to 50 for IPsec datagram using ESP protocol, so this way the routers actually understand that this is an IPsec datagram, but not an ordinary IP datagram. The routers on the internet, IPsec datagram is processed as an ordinary datagram, so the ultimate destination of the datagram is perceived as R2. All of the routers in the middle think that this message is sent to R2. So let's look at the enchilada ingredients. The fields in the ESP trailer, padding length, and the next header. Padding ensures that the resulting message is an integer number of blocks by inserting meaningless bits. We talk about this. Generally what we prefer is a single bit of 1 and the remaining bits are filled with zeros. Pad length tells the receiving entity how much padding was inserted, thus how much needs to be removed. Next header identifies the type of data contained in the payload data field, like UDP and so on. Let's look at the ESP header. It contains SPI and sequence number. The SPI field tells the receiving entity the SA to which the datagram belongs. So from this, the router knows which keys and which algorithms they need to use. And the receiving entity intakes its SAD with the SPI to determine appropriate authentication and decryption algorithms and keys. The same thing that I said. The sequence number here is necessary to prevent replay attacks. So router actually checks if the sequence number was already received and so on. So let's summarize it again. So an IPsec datagram sent from R1 to R2. So R2 receives the IPsec datagram, checks the protocol field, the leftmost IP header, so sees that it is 50, so R2 applies the IPsec ESP processing to the datagram. R2 uses the SPI to determine which SA the datagram belongs to. R2 calculates the MAC of the enchilada and verifies that the MAC is consistent with the value in the ESP MAC field, so this way authentication is performed. And R2 makes sure that the enchilada comes from R1. Again, this is what this MAC is used for. R2 checks the sequence number field to verify that datagram is fresh, so it's not replayed. R2 decrypts the encrypted units using SA's decryption algorithm and key. It removes padding, extracts original IP datagram. So now this router knows which IP this data is sent to and sends it to the IP which is inside the branch office. So let's talk about key management. For two routers, R1 and N2, SA information is easily inserted into the SADs of the endpoints. Reminder, SA information includes encryption, authentication algorithms and keys and the SPIs. But for very large networks, this might be some kind of a burden. If there are too many routers, it would be hard to perform the key management. So in this kind of scenarios, we can use the Internet Key Exchange algorithm. This protocol can be reached from here, but it is similar to SSL handshake. So to summarize, what services does IPsec provide? Assumption is Trudy does not know the authentication and encryption keys used by the SA, which is actually valid assumption is there are not any backdoors in the routers and so on. Trudy cannot see the original datagram because it is encrypted, but also the protocol number, source, the destination IP addresses and so on. No knowledge of what datagram is carrying, so TCP or UDP, the listener doesn't know this, as well as the type of application data like HTTP, SMTP, because all of the payload is encrypted. So for this reason we say confidentiality provided by IPsec is much better than confidentiality provided by SSL, but this sentence shouldn't be taken out of context. We are trying to say this. I mean, we are not trying to say that the encryption algorithm used in IPsec is better than the SSL. Most probably you are using the same algorithm like AES with the same link key. So here the security doesn't come from the cryptography you are using. Here we say that it provides more confidentiality because of the above sentences, because the person who's listening to the communication doesn't know the source and destination IP address, protocol number, type of datagram, and so on and so forth. So this sentence trying to say this. Otherwise, this doesn't mean that instead of using SSL, just use IPsec. This is not the case, because IPsec is secured at the network layer, but here you have secured at the transport layer, or maybe application layer, depending on how you perceive it. Okay, so you cannot only survive with IPsec, you need SSL at the end. Moreover, truth is not able to tamper the datagram by flipping its bits, because the MAC-based integrity chain would fail. Truth isn't able to masquerade as R1 by creating an IPsec datagram with the source and destination address. The datagram fails the integrity check because it doesn't have the keys. And truth is not able to conduct a replay attack because IPsec includes sequence numbers, and routers check if the sequence number is fresh or not. So to summarize, IPsec provides confidentiality, source authentication, data integrity, and replay attack prevention, but don't forget that it is at the network layer, not application or at the transport layer. So I think this concludes our discussion of the security at the internet layers that we are talking about so far. So we concluded application layer security, transport layer security, and network layer security.